Our next optimization problem that we're going to look at takes a look at boxes. If we are going to make a box out of a sheet of cardboard, we're going to make this box with no lid. We're going to have to cut out of the corner so that we can fold those squares, those sides up on these dotted lines. And when you do, you should end up with, folding up those sides, a box with no lid. But what we want to do is maximize the volume of this box. So how big of a cut do we need to make? Well, we'll say that the cuts are going to be squares, x by x, so that the sides all match up. And then we're going to have a length of the box and a width of the box originally before we cut those x's out. When we cut out those x's, those sides for the length and width, because an x has been cut out of both sides, there's been 2 x's cut out of the width. So it's the width minus 2x. And the length has 2 x's cut out of the length. So it's going to be the length minus 2x. And then the x's that cut is going to be the height of the box. And we know that volume is equal to length times width times height. Multiplying these together, you get x times w minus 2x times the length minus 2x. That is the volume that we're going to try and maximize. So if I'm going to take a box to be made out of a sheet of a cardboard, that is 6 inches by 9 inches, by cutting squares out of the corner, like we did in the picture above here, what size square will maximize the volume? So just like our picture above, we've got a rectangular sheet of cardboard. We're going to be cutting squares out of the corners. Then we're going to fold up on the dotted lines to make our box. The dimensions of this box, though, were 9 by 6. Before we cut out an x from each side of the 6. And we cut out an x from each side of the 9. So just like our equation above found, the volume is going to be equal to the x. It's going to end up being the height of the box. The 9 had 2 x's cut out of it, so now it's 9 minus 2x. And the 6 had 2 x's cut out of it, so now it's 6 minus 2x. That volume is what we want to maximize. So we're going to take the derivative and set it equal to 0. But before we take the derivative, let's clean this up with a little bit of algebra. I'm going to multiply out the binomials first. 9 times 6 is 54. 9 times negative 2 is negative 18x. 6 times 2 is negative 12x. And negative 2 times negative 2 is positive 4x squared. Let's combine like terms and put the 4x squared in the front, giving us negative 30x in the middle, plus 54. And then when I distribute the x through, we get 4x cubed minus 30x squared plus 54x. That's the formula for the volume. We're going to take the derivative of the volume with respect to x to find our maximized volume. The derivative is 12x squared minus 60x plus 54. That's what we want to set equal to 0 in order to find our maximum point. Well, to help out with the solving, I'm going to divide everything by, it looks like I can divide everything by 6, just to get smaller numbers to work with. This step's technically optional, but it does make the numbers easier to work with. That's going to leave me with 2x squared minus 10x plus 9 equals 0. And I don't think that is going to factor, but that's OK because we have our quadratic formula that x is equal to the opposite of b plus or minus the square root of b squared minus 4ac all over 2a to help us solve. When I do that, we get 10 plus or minus the square root of 100 minus 72, which is 28 over 4. So we've got a plus and we've got a minus. Let's do the plus first. So if I do on my calculator, 10 plus the square root of 28. Make sure I hit enter so that I don't mess up order of operations. 10 plus the square root of 28 equals. Divide that answer by 4, and I get approximately 3.823. If I do the minus, 10 minus the square root of 28, hit enter on my calculator, divide by 4, and I get 1.177. So I have two possible answers for the size of my cut. But I need to be careful. Think back to my box. The smallest dimension was the 6. And if I'm cutting in on both sides, the most I can cut in before I'm just cutting the box in half is 3. So we can't cut more than 3. We probably don't want to cut 3 either, because you don't get much of a box by cutting it in half. So the first answer of 3.823 is too big. We can't cut that far, which means we need to cut out squares with side length of 1.177 inches. That will optimize our box's volume. In our next video, we're going to continue working with these optimization examples.